Heat is all around us. It's the warmth of the sun on our skin, the comforting heat from a cup of tea, and the fiery inferno of a raging wildfire. This invisible force, known as thermal energy, is constantly in motion, flowing from hotter objects to cooler ones. Understanding how this dance of heat unfolds is crucial for comprehending a wide range of phenomena, from the weather patterns that govern our planet to the technology that powers our daily lives. Imagine a hot cup of coffee left on a table. Over time, the coffee cools down, while the surrounding air slightly warms up. This simple observation illustrates the fundamental principle of thermal energy transfer. Heat always flows from a region of higher temperature to a region of lower temperature, striving to achieve a state of thermal equilibrium. This transfer of thermal energy can occur through three main mechanisms: conduction, convection, and radiation. Each mechanism involves different processes at the molecular level, dictating how heat travels through solids, liquids, gases, and even the vacuum of space. Join me as we delve into the fascinating world of thermal energy transfers, uncovering the microscopic secrets behind this fundamental force of nature. To truly grasp the concept of thermal energy, we must first venture into the microscopic realm and examine the building blocks of matter molecules. These tiny particles are in constant motion, vibrating, rotating, and translating, their movements a reflection of their inherent thermal energy. The state of matter, solid, liquid, or gas, dictates the freedom and nature of these molecular movements. In solids, molecules are tightly packed, their arrangement resembling a well-ordered lattice. They are confined to fixed positions, only allowed to vibrate around these equilibrium points. Imagine a group of people tightly packed in a crowded train, each individual swaying slightly but unable to move freely. Liquids, on the other hand, grant their molecules more freedom. While still close together, these particles can now move around each other, flowing and adapting to the shape of their container. Think of a group of people navigating a busy street, bumping into each other but able to move past. Gases provide the ultimate freedom of movement for molecules. These particles are widely spaced, zipping around randomly and colliding with each other in the walls of their container. They are like a swarm of bees buzzing around a hive, each individual moving independently. This microscopic perspective on the states of matter is crucial for understanding how thermal energy manifests itself and how it is transferred between different materials. The freedom of movement and the interactions between molecules dictate the efficiency of heat transfer and influence the thermal properties of materials. Imagine holding a feather in one hand and a rock of the same size in the other. The rock feels much heavier even though both objects occupy the same amount of space. This difference in heaviness for a given volume is what we call density. In essence, density describes how tightly packed the matter is within a given space. We can express this concept mathematically with a simple formula. Density, Rho, equals mass, m, divided by volume, v. This equation tells us that denser materials have more mass packed into the same volume. For instance, a gold bar feels much heavier than a chocolate bar of the same size because gold atoms are much more densely packed than the sugar and cocoa molecules in chocolate. Understanding density is crucial for comprehending various phenomena related to thermal energy transfer. For example, convection, a key heat transfer mechanism in fluids, relies on density differences. As a fluid is heated, its density typically decreases, causing warmer, less dense fluid to rise and cooler, denser fluid to sink. This continuous cycle drives convection currents, distributing heat throughout the fluid. Section 4. Temperature, measuring the intensity of heat. We often use the words heat and temperature interchangeably, but in the realm of physics, they hold distinct meanings. While heat refers to the total energy transferred between objects due to a temperature difference, temperature is a measure of the average kinetic energy of the particles within a substance. Think of it this way. Imagine two pots of boiling water, one small and one large. Both pots have the same temperature, 100 degrees Celsius, because the water molecules in both pots have the same average kinetic energy. However, the larger pot contains more water molecules and therefore more total thermal energy. To measure temperature, we use scales like Celsius and Kelvin. The Celsius scale is based on the freezing and boiling points of water, setting 0 degrees Celsius as the freezing point and 100 degrees Celsius as the boiling point at standard atmospheric pressure. The Kelvin scale, on the other hand, starts at absolute 0, the theoretical temperature at which all molecular motion ceases. Converting between Celsius and Kelvin is straightforward. Kelvin equals Celsius plus 273.15. Understanding temperature is crucial for comprehending how heat flows and for quantifying the amount of thermal energy transferred during various processes. It provides a standardized measure of the hotness or coldness of an object, allowing us to predict and control the direction and rate of heat transfer. Section 5. Kinetic energy, the microscopic basis of temperature. At the heart of the concept of temperature lies the kinetic energy of molecules. Kinetic energy is the energy of motion, and even within seemingly still objects, the constituent molecules are in constant motion, vibrating, rotating, and translating. The faster these molecules move, the higher their kinetic energy, and the higher the temperature of the substance. This relationship between temperature and the average kinetic energy of particles can be expressed mathematically. Average kinetic energy equals 3/2 times the Boltzmann constant times temperature. This equation highlights a fundamental principle. Temperature is a direct measure of the average kinetic energy of the particles within a substance. As temperature increases, the molecules move faster and collide more frequently, transferring energy to each other and to their surroundings. This microscopic dance of molecules, driven by their kinetic energy, underpins the concept of thermal energy and its transfer. By understanding the relationship between temperature and kinetic energy, we gain a deeper appreciation for the fundamental processes that govern the flow of heat.